Hello, my name is Stephen White. There's my ID for you. I've decided to do the physiology of tumors. So we are just going to dive in. So I want to start with talking about the microenvironmental physiology of tumors. I do want to note that it is much more hostile compared to normal tissues. They definitely differ because with tumors, you will see hypoxia, which is a lack of oxygen, and it does play a big role because it will reduce fixation of radiation and it can induce DNA damage. It does provide difficulties when treating cancer, as we will see further in. Another huge aspect is the tumor vasculature that causes a hostile environment, and this is the channels of tumors nutrition supply. And it is also the tumor cell dissemination, which plays a role in growth and metastasis. Now, hypoxia is a big key here for the difference from normal tissues, and it does play a huge role in how efficient our cancer treatment is for tumors. You'll see that tumor cells will have high glucose and energy deprivation and high lactate levels. And then it will also present extracellular acidosis, and the hypoxia microenvironment can resist irradiation treatment, meaning that we can see the treatment failure for tumors. So the hypoxia paired with the very weak vasculature and the extracellular acidosis, all of these compound into being a very difficult thing to treat, considering it is vastly different from normal tissues. So it does tend to require a different approach, and it does tend to require you to think outside of the box. So if we're looking at this, you can see blood vessel at the top, and then you have normal aerobic cells. And then under that, you do have hypoxic viable cells. So these are going to be lacking oxygen. And at the bottom, you have necrotic or dying or dead cells. And as you move down this, you see that as we get further and further away from healthy blood vessels and healthy cells, you are going to see increasing chemotherapy and radiation resistance. Now, next, I want to talk about the physiology of solid tumors. And this is where we're going to touch on the biggest key, vasculature, the difference between tumors and normal cells. Now, we can see that in tumors, you will have distended capillaries, leaking wells, and sluggish flow. So we will have a difference in blood vessels, which can cause problems for cancer treatment when you look at the hypoxia. And then the growth does rely on angiogenesis and vessel growth. And we'll see that hypoxia is actually a great way to treat cancer. And then this image is just going over the different comparison between how normal healthy tissues will look compared to tumor tissues. So you can see that there's a huge difference between those capillaries. You'll see leakiness, collapsed or narrowed vessel lumens, low perfusion, and then you'll have low blood flow and limited oxygen delivery, which ends up bringing to hypoxia, which ends up bringing to acidity. Next, I want to touch on the glycolysis and mitochondrial physiology relating to tumors. So with glycolysis and the mitochondrial physiology in relation to tumors, you'll see that cellular metabolism is a sign for cancer that you want to keep a close eye on and how it is functioning and whether it is normal or not. In tumors, you will see increased aerobic lactic production as well as LDH protein tumors. And tumor cells do depend on glucose metabolism since there is a lack of oxygen, and the mitochondrial physiology specifically, and the LDH proteins. And the LDH proteins do have importance relating to tumorigenicity. LDH deficient cells have much lower LDH, which is a key role in tumor maintenance. LDH catalyzes the interconversions of pyruvate and lactic acid, and it also deals with the interconversion of NADH. And I want to return to hypoxia, and I want to touch on how we can use hypoxia actually to treat cancer. So we can use hypoxic selective cytotoxins gene therapy, or we can also inhibit angiogenesis. And that's an important part to know the physiology is because we can realize we can inhibit angiogenesis, we can inhibit the growth of tumors. So something that is so strong a strength for tumor growth and cancer development, that state of being hypoxic, it is also actually a strength that we can use in treating it. Now, I want to move on to LLPS in cellular physiology and tumor biology. LLPS stands for liquid lipid phase separation. It is a mechanism that has been used to explain the formation of organelles and membraneless, oh, membraneless, sorry, membraneless condensates. LLPS can be used to increase the efficacy of cancer therapy by restoring that chemosensitivity of cancer cells by using MED1 condensates and resistant cancer cells. So we learned earlier that as we move down and get more hypoxic and the extracellular acidosis continues, you do see that there's increasing chemotherapy and radiation resistance. This is a way to negate that effect and reintroduce those tumor cells being perfectly vulnerable to those cancer therapies. So this is a good way to make our treatments that we have currently more efficient and more effective. And then we do have three physiological barriers in delivering antibodies to the tumor. So when delivering antibodies to the tumors and other macromolecules, the three mains are heterogeneous blood supply, which limits delivery of blood-borne molecules to well-perfused areas. And the next is an elevated interstitial pressure, which will reduce extravasation of fluids and macromolecules. And it also affects readily outward convection, which opposes inward diffusion, which just means that we will have a decrease in the amount of antibodies and macromolecules that will be able to even deliver to the tumor. And then last, I want to touch on the large transport distance in the interstitium. So these large distances will increase the time for slower macromolecules to reach distal regions of the tumor, which are farther away. So you are having a lot slower process of delivering these antibodies, and it's not going to be as quick. And for something as tumors that move quickly and growth and progress rapidly, we want the most efficient and the quickest way of, using our cancer therapies. These are my references for all my sources. And then here I have my references for the images. The first one is for image 1 and the second one is for image 2. And that concludes my presentation. Thank you.